Look up at the night sky, and you're not just seeing stars, you're staring into a time machine. Every glimmer of light carries echoes from the distant past, but none are more ancient or mysterious than the cosmic microwave background. This faint glow, often called the CMB, is the oldest light in the universe, a ghostly whisper from a time when everything was just beginning. It's the afterglow of the Big Bang itself, lingering in the void for over 13 billion years, and it holds secrets that rewrite our understanding of reality. Imagine holding a photograph taken just moments after the universe was born. That's what the CMB is, a snapshot frozen in time, revealing the fiery infancy of existence. Stretching across the entire cosmos, this delicate radiation carries the fingerprints of the first structures that would one day become galaxies, stars, and even us. But here's the wild part: this light isn't just a relic. It's still shaping the universe today, guiding the dance of matter and energy on scales so vast they defy comprehension. Why should this matter to you? Because hidden in that faint microwave static are answers to the biggest questions we can ask. How did the universe start? What is it made of? And perhaps most hauntingly, what fate awaits it all? Over the next 30 revelations, we'll unravel the astonishing science behind this primordial light, from how it was accidentally discovered by two puzzled radio astronomers to the way it's helping us decode the invisible forces that govern reality. Buckle up, we're about to trace the universe's oldest light back to the very dawn of time. The cosmic microwave background isn't just ancient light, it's the universe's birth certificate. Picture this: 13.8 billion years ago, the Big Bang flooded the cosmos with searing radiation. As space expanded and cooled, that blazing energy stretched into longer, weaker wavelengths, leaving behind a faint microwave whisper that now blankets everything. No matter where you point a radio telescope, you'll find this glow, nearly identical in all directions, like the universe's oldest wallpaper. But the story of its discovery is as fascinating as the light itself. In 1965, two radio astronomers named Arno Penzias and Robert Wilson were troubleshooting a persistent hiss in their antenna at Bell Labs in New Jersey. No matter how they adjusted the equipment or cleaned out pigeon nests, the noise wouldn't vanish. What they'd stumbled upon wasn't a technical glitch, it was the echo of creation itself. Their accidental detection of the CMB earned them a Nobel Prize and confirmed a groundbreaking prediction. If the universe began in a fiery explosion, its cooling remnants should still be detectable. This faint signal, just 3 degrees above absolute zero, is more than a relic, it's a time capsule. The slight variations in its temperature, smaller than 1 part in 100,000, are the seeds of everything. Those tiny fluctuations became the gravitational wells where galaxies eventually formed. Every star, every planet, even you, exist because of those subtle ripples in the early universe. The CMB doesn't just tell us where we came from, it's a roadmap of how structure emerged from chaos. And here's the mind-bending part. This light has been traveling since the universe was a mere 380,000 years old, back when space was so dense and hot that atoms couldn't even form. It's the moment when the cosmos finally became transparent, releasing this glow like a cosmic first breath. Today, we're not just observing ancient history, we're deciphering the universe's baby pictures. That faint glow filling the cosmos doesn't just carry ancient light, it holds an astonishing chill. At a mere 2.7 degrees above absolute zero, the cosmic microwave background is colder than deep space itself. But here's what makes that number so extraordinary. This uniform temperature blankets the entire observable universe, from one distant galaxy cluster to another, with variations smaller than 100,000th of a degree. Think about that for a moment. If the Big Bang was a violent, chaotic explosion, why isn't the afterglow patchy? How could regions now separated by tens of billions of light years share nearly identical temperatures when there hasn't been enough time since the universe began for heat to spread that evenly? This horizon problem baffled scientists for decades. The answer lies in a process so rapid it sounds like magic cosmic inflation. In the first trillionth of a second after the Big Bang, the entire observable universe may have been smaller than a single atom. Then, in an unimaginable growth spurt, space itself expanded faster than light could chase it, stretching quantum fluctuations into the slight temperature variations we see today. This hyper-fast smoothing explains the CMB's eerie uniformity while simultaneously planting the seeds for galaxies to form later. But the cooling tells another story too. When this light first broke free 380,000 years after the Big Bang, it blazed at around 3,000 degrees Kelvin, hot enough to ionize atoms. As the universe expanded over billions of years, that light stretched into longer, weaker microwave wavelengths, cooling to today's faint whisper. Each photon we detect has been redshifted by the expansion of space itself, carrying a cosmic barcode of the universe's growth. What's truly remarkable is how precisely we've measured this chill. Satellites like COBE and Planck have mapped the CMB's temperature with such sensitivity they can detect variations equivalent to millionths of a degree. Those microscopic fluctuations are the universe's genetic code, showing where matter began clumping together under gravity's pull. Without that fine-tuned cooling and expansion, stars might never have ignited, and the cosmic story would have ended before it began. This 2.7 Kelvin glow isn't just a number. It's one of cosmology's most vital clues, revealing how perfectly balanced the early universe had to be for us to exist at all. The cosmic microwave background doesn't just show us the universe's past, it's the ultimate baby picture, capturing the precise moment when the cosmos transitioned from a glowing plasma to a transparent expanse. Imagine developing a photograph taken when the universe was only 380,000 years old. That's exactly what scientists did with satellite maps of the CMB. These intricate color-coded images reveal temperature variations so subtle they'd be imperceptible to human eyes, fluctuations smaller than 1 part in 100,000, yet these minute differences hold the blueprint for everything we see today. In that primordial glow, slightly warmer patches indicate regions where matter was beginning to clump together under gravity's pull, while cooler spots mark emptier voids. Over billions of years, those tiny overdensities grew into the sprawling cosmic web of galaxies and superclusters we observe now. Every galaxy cluster, every swirling nebula, even our own Milky Way originated from these faint imprints. It's like finding the pencil sketch beneath a finished oil painting, the universe's first rough draft. What makes this baby picture so remarkable is its predictive power. The statistical patterns in those temperature fluctuations match theoretical models of the early universe with astonishing precision. Scientists can literally calculate how much dark matter must exist, how fast space is expanding, even the universe's total curvature, all from decoding this ancient light. The CMB doesn't just show us infant structures, it confirms fundamental physics on the grandest possible scale. Yet mysteries remain. Some large-scale patterns in the CMB appear unexpectedly smooth, while certain alignments dubbed the axis of evil by researchers challenge standard cosmological models. These anomalies hint that our understanding of the universe's first moments might still be incomplete. That baby picture contains wrinkles we're only beginning to interpret as cosmic puzzles wrapped in microwave light. Most astonishingly, this snapshot isn't static. As the universe ages, the CMB continues fading and cooling. Future civilizations billions of years from now might struggle to detect it at all. We're living in a privileged era where the afterglow of creation remains bright enough to study, a fleeting window to witness our cosmic origins before the evidence vanishes into the expanding dark. One of the most baffling features of the cosmic microwave background is just how eerily uniform it appears. No matter which direction astronomers point their telescopes, they measure the same temperature, at 2.7 degrees above absolute zero, with variations so minuscule they're barely detectable. These fluctuations amount to just 1 part in 100,000, like detecting a single grain of sand in a beach full of identical grains. But this near-perfect uniformity shouldn't be possible, and it took a revolutionary idea to explain why. Imagine pouring a cup of hot coffee into an icy lake. Over time, the heat would spread until the entire body of water reached the same temperature. But here's the problem: the observable universe is so vast that even at light speed, there hasn't been enough time since the Big Bang for heat to travel from one distant region to another. Yet somehow, the CMB's temperature is nearly identical everywhere we look. This horizon problem suggests that regions now billions of light-years apart were once in close contact, exchanging energy before being violently separated. The solution came with the theory of cosmic inflation, a mind-bending concept where the infant universe expanded exponentially faster than the speed of light for a fraction of a second. During this hyper-accelerated growth spurt, what was once a tiny, homogeneous patch of space got stretched across the entire cosmos, locking in that uniform temperature before regions could drift out of touch. It's like inflating a balloon with a perfectly smooth pattern drawn on it. No matter how much you stretch the surface, the pattern remains consistent. But those 1 in 100,000 variations tell their own story. They aren't random noise, they're the faint imprints of quantum fluctuations from the universe's first moments, magnified by inflation into the seeds of cosmic structure. Without these microscopic ripples, gravity would have had nothing to work with, and galaxies might never have formed. The CMB's uniformity isn't just a curiosity, it's evidence of a process so precise that even the tiniest deviations were enough to build everything we see today. This delicate balance between sameness and variation is what makes the cosmic microwave background such a powerful tool. It reveals a universe that began smooth but not perfectly smooth, ordered but not rigid, a cosmic Goldilocks zone where conditions were just right for complexity to emerge. And tucked within that near-uniform glow are clues to mysteries we're still unraveling, from dark energy's influence to the ultimate fate of space itself. Those barely perceptible temperature variations in the cosmic microwave background aren't just static. They're the universe's architectural plans written in heat signatures. When scientists first mapped these fluctuations with satellites like CMB and Planck, they weren't just seeing random noise. They were staring at the gravitational scaffolding for everything: galaxy clusters, supervoids, even the vast filamentary structures that weave the cosmos together. Here's how it works. Every slightly warmer patch in the CMB marks a region where matter was marginally denser in the early universe. Over billions of years, gravity amplified those tiny overdensities, pulling in surrounding gas and dark matter until they collapsed into galaxies. Conversely, the cooler spots correspond to underdense regions that evolved into the cosmic voids we see today: gigantic empty spaces spanning hundreds of millions of light-years. It's like watching time-lapse footage of a city rising from bare Earth, where the first uneven patches of dirt predict where skyscrapers will eventually stand. The precision of this cosmic blueprint is staggering. Those 1 part in 100,000 temperature differences translate into density variations of just 0.001%, yet that was enough for gravity to sculpt the entire observable universe. Modern simulations can trace the growth of these fluctuations from the CMB's snapshot all the way to the present-day cosmic web, matching actual galaxy surveys with uncanny accuracy. The patterns align so perfectly that researchers can predict where undiscovered galaxy clusters should exist based solely on the CMB's ancient fingerprints. But the real revelation lies in what these fluctuations tell us about invisible forces. The distribution of warm and cold spots reveals how dark matter, the universe's hidden skeleton, must have behaved to create the structures we see. Their spacing acts like a cosmic ruler, measuring the universe's expansion rate and curvature. Even the slight asymmetry in fluctuation sizes between hemispheres hints at deeper mysteries, possibly evidence of primordial magnetic fields or exotic physics before inflation. What's humbling is realizing we're literally made from these imperfections. The atoms in your body were once part of those slightly denser regions in the CMB, drawn together over eons by gravity's patient pull. The universe could have been perfectly smooth, a featureless sea of particles, but instead, it chose to clump just enough for stars, planets, and life to emerge. Those microscopic ripples weren't flaws, they were the first strokes of a masterpiece still being painted. The cosmic microwave background doesn't just map the universe's infancy, it reveals the very shape of reality itself. One of the most profound discoveries hidden in those microwave patterns is this: our universe appears to be geometrically flat. Not flat like a sheet of paper, but flat in the cosmic sense, where parallel light beams stay perfectly aligned across billions of light years instead of converging or diverging over time. This revelation comes from carefully measuring the apparent size of temperature fluctuations in the CMB. Think of it like cosmic trigonometry. By calculating how much these hot and cold spots appear stretched or compressed across the sky, scientists can determine whether space curves back on itself like a sphere, bends outward like a saddle, or remains perfectly flat. The data from satellites like WMAP and Planck show these fluctuations match precisely what we'd expect in a flat universe, with a margin of error less than 1%. A flat universe isn't just a geometric curiosity, it's a critical prediction of cosmic inflation. During that explosive expansion in the universe's first moments, any initial curvature would have been stretched so dramatically that the observable cosmos today would appear indistinguishable from flat, much like how a tiny section of an enormous balloon feels flat to an ant crawling on its surface. The CMB's flatness measurement is like finding the receipt for inflation's shopping spree, evidence that space underwent this hyper-fast stretching. But flat here has mind-bending implications. It doesn't mean the universe is two-dimensional or has an edge. Instead, it describes how gravity and light behave on cosmic scales. In a flat universe, the total mass-energy density is perfectly balanced at what cosmologists call the critical density, approximately 5 protons worth of matter per cubic meter of space. This exact balance determines whether the cosmos will expand forever or eventually collapse. What's astonishing is how perfectly the numbers align. Ordinary matter, the stuff of stars and planets, accounts for less than 5% of this critical density. Dark matter makes up about 27%, while the remaining 68% is dark energy. These proportions, deduced from the CMB's fluctuations, add up to precisely the amount needed for flatness. It's as if the universe signed its name in microwave light, confirming the inflationary Big Bang model's most audacious claim. Yet this flatness raises profound questions about our cosmic home. If space isn't curved, does that mean the universe is infinite? Could there be other bubble universes beyond our observable horizon with entirely different physics? The CMB gives us answers while pointing to even deeper mysteries, reminding us that even a universe called flat is anything but ordinary. Those faint microwave whispers from the dawn of time don't just show us the universe's baby pictures, they act as the most precise cosmic clock ever discovered. By decoding the subtle patterns in the cosmic microwave background, scientists have pinned down the age of our universe with astonishing precision: 13.8 billion years, give or take a mere 40 million. That's like knowing the exact minute someone was born after tracing their family history back thousands of generations. Here's how this cosmic detective work unfolds. The CMB's temperature fluctuations serve as frozen sound waves from the early universe, captured in the moment when matter and light finally went their separate ways. Imagine dropping pebbles into a pond. The ripples spread outward in predictable patterns based on the water's properties. Similarly, those primordial density variations created acoustic oscillations that left distinct imprints in the microwave background structure. The spacing between these ripples acts like a rigid ruler etched into space itself, unaffected by later cosmic events. Satellites like Planck have measured these patterns so precisely that cosmologists can run the universe's expansion backward like rewinding a film reel. By accounting for how dark energy accelerates expansion and how dark matter slows it through gravity, they calculate exactly how long it took for space to stretch from a hot, dense singularity to the vast cosmos we see today. The math checks out multiple ways, from the CMB's fluctuation sizes to the ratio of hydrogen isotopes formed in the first few minutes. All roads lead to that same staggering number, 13.8 billion. What's extraordinary is how this lifespan fits other independent measurements. The oldest stars observed in globular clusters, dating techniques using radioactive decay in meteorites, even the motion of galaxies all converge on similar timelines. But the CMB provides the cleanest stopwatch because it records the universe's condition before stars or galaxies muddied the waters. It's like finding an untouched archaeological layer beneath centuries of civilization, a pristine snapshot of time zero. Yet this precise age isn't just a number, it's a boundary for reality itself. Knowing the universe has existed for 13.8 billion years tells us how far light could have traveled, placing hard limits on the observable cosmos's size. It defines when the first stars could have ignited, when planets could have formed, even how many generations of supernova were needed to forge the heavy elements in your bones. That microwave glow isn't just ancient light, it's the ultimate birth certificate, stamped with the exact moment everything began. Beneath the temperature variations of the cosmic microwave background lies another layer of secrets, hidden patterns in the light's very orientation. This phenomenon, called polarization, turns the CMB into more than just a thermal snapshot. It becomes a dynamic record of the universe's most violent birth pangs. Just as sunlight reflecting off water becomes polarized, those primordial photons scattered off electrons in the early universe, imprinting a faint directional signature that carries clues about everything from inflation's gravitational waves to dark matter's influence. The most thrilling possibility locked in this polarization is evidence of cosmic inflation's gravitational waves. Picture the infant universe undergoing that exponential expansion, space itself stretching faster than light could travel. Such a cataclysmic event wouldn't just smooth out temperatures, it would send ripples through space-time itself like tremors from a cosmic earthquake. These gravitational waves would have jostled the plasma of the early universe, leaving a distinctive swirling pattern in the CMB's polarization known as B modes. Detecting them would be like finding the fingerprints of inflation's mechanism, confirming that the universe really did undergo that unimaginable growth spurt. But polarization doesn't just whisper about inflation, it shouts about structure. As the first atoms formed and photons began their 13 billion-year journey, they scattered off electrons in a process called Thomson scattering. This created two types of polarization patterns, E modes, which mirror the density variations seen in temperature maps, and the more elusive B modes. E modes help trace how matter clumped together under gravity, while B modes could reveal the universe's earliest gravitational disturbances. Together, they form a cosmic Rosetta Stone, allowing scientists to cross-check theories of dark matter, neutrino masses, and even the universe's reionization phase when the first stars ignited. The hunt for these signals has driven some of cosmology's most ambitious experiments. Telescopes at the South Pole, high-altitude balloons, and space missions like Planck have all scrutinized the CMB's polarization with increasing precision. In 2014, the BICEP2 team initially reported detecting primordial B modes, a potential smoking gun for inflation, only to later find interstellar dust might have mimicked the signal. This kind of meticulous detective work shows how polarization studies demand near-impossible levels of precision, separating cosmological truths from galactic interference. What makes polarization so revolutionary is its dual nature. It's both a snapshot of the universe's toddler phase and a window into its first infinitesimal moments. While temperature maps show us the universe at 380,000 years old, polarization patterns could illuminate events that occurred a trillionth of a second after the Big Bang. It's the difference between studying a fossil and witnessing the creature's last heartbeat. One shows the aftermath, while the other captures the dynamism of creation itself. Yet the full story remains half-written. Future observatories like the proposed CMB Stage 4 project aim to map polarization with such sensitivity they might finally catch inflation's gravitational waves in the act. Success would rank among science's greatest achievements, proving that the universe really did expand faster than light, and that space-time itself trembles with echoes from before time had meaning. Every photon's subtle twist carries a message. The cosmos isn't just expanding, it's vibrating with the memory of its own spectacular birth. Sometimes the most groundbreaking discoveries happen when you're not even looking for them. That's exactly how Arno Penzias and Robert Wilson stumbled upon the cosmic microwave background, a hiss in their radio antenna that refused to go away. What began as a frustrating technical glitch turned into one of the 20th century's greatest scientific breakthroughs, earning them the 1978 Nobel Prize in Physics and forever changing how we understand the universe's origins. Their story reads like a cosmic detective novel. Working at Bell Labs in New Jersey, the two astronomers were troubleshooting an unusually persistent noise in their horn-shaped antenna, a device designed to study radio waves from space, not cosmic relics. No matter how they adjusted the equipment, cleaned out pigeon nests, or recalibrated their instruments, that faint microwave hiss remained. It came from every direction, day and night, with no apparent source. What they'd accidentally detected wasn't interference, it was the faint afterglow of the Big Bang itself, still reverberating across the cosmos after billions of years. The timing couldn't have been more serendipitous. Just 40 miles away at Princeton University, a team led by physicist Robert Dicke was actively searching for this very signal, a predicted remnant of the universe's fiery birth. When Penzias and Wilson called Dicke to describe their mysterious noise, he reportedly turned to his colleagues and said, "Well, boys, we've been scooped." The pieces fit perfectly. Their accidental discovery matched theoretical predictions that a universe born from a hot, dense explosion should still carry a cooled thermal echo. This wasn't just another scientific achievement, it was the smoking gun for the Big Bang theory. Before the CMB's detection, cosmology was locked in a heated debate between supporters of the Big Bang and proponents of the rival steady-state model, which argued the universe had no beginning. Penzias and Wilson's static-filled data settled the argument conclusively. Their Nobel Prize didn't just honor their technical skill, it validated an entirely new way of seeing reality, proving the universe had a definitive birth moment we could still observe today. What's often forgotten is how humble the discovery appeared at first. Their original 1965 paper in the Astrophysical Journal was just 800 words long, with the understated title, "A Measurement of Excess Antenna Temperature at 4,080 megacycles per second." No grand claims, no mention of the Big Bang, just meticulous documentation of a puzzling signal. Yet that quiet observation unlocked doors to questions humanity had asked for millennia. Where did everything come from? How did it all begin? The true brilliance of their work lies in its simplicity. Unlike many Nobel-winning experiments requiring billion-dollar colliders or satellites, Penzias and Wilson used repervised communications equipment to listen to the universe's oldest story. Their discovery reminds us that sometimes the answers to cosmic mysteries aren't hidden in distant galaxies or complex equations. They're written in the faintest whispers, waiting for someone patient enough to listen. The cosmic microwave background didn't always glow in invisible microwaves. It began as scorching visible light, blazing across the infant universe in brilliant shades of orange and yellow. What we detect today as faint microwave static was once vibrant enough to outshine 10,000 suns, transformed over billions of years by one of the cosmos' most fundamental processes, redshift. This relentless stretching of light waves is the universe's way of scribbling its expansion history into every photon we observe. When the CMB first broke free 380,000 years after the Big Bang, space was still dense with plasma, glowing at about 3,000 degrees Kelvin, similar to the surface of a red giant star. Those photons danced across a universe smaller than a grain of sand compared to today's vast expanse. But as space itself stretched during the eons that followed, it dragged the light waves along with it, elongating their wavelengths like taffy pulled to infinity. What started as visible light gradually shifted through infrared into the microwave spectrum we detect now, with wavelengths measured in centimeters rather than nanometers. The math behind this transformation is astonishingly precise. The universe has expanded by a factor of about 1,100 since recombination, meaning every photon's wavelength stretched by that same amount. That's why the once searing 3,000-degree glow cooled to a mere 2.7 degrees above absolute zero, a direct consequence of space's relentless growth. This redshift isn't just a curiosity, it's the universe's most honest speedometer, revealing exactly how much stretching occurred between the CMB's origin and our telescopes. But redshift does more than just cool the light, it preserves a cosmic timeline in every wavelength. Imagine each photon as a mile marker on an infinite highway, recording how much the road has lengthened since it was planted. By measuring how much the CMB's light has redshifted, cosmologists can reconstruct the expansion rate at every epoch, catching subtle changes caused by dark energies accelerating push or dark matter's gravitational pull. It's like finding growth rings in a tree where each ring encodes the weather conditions of a particular year, except here the tree is space-time itself. What's truly humbling is realizing this process never stops. The microwaves we detect today will continue redshifting into even longer radio waves over billions of years. Future civilizations, if any still exist, might search for this relic not with microwave antennas but with radio telescopes, listening for whispers from an era when the universe glowed not with stars, but with the fading embers of its own spectacular birth. Even the cosmic microwave background, our most pristine map of the early universe, has its strange quirks. Among them, the so-called axis of evil stands out as one of cosmology's most tantalizing puzzles. This eerie alignment, where certain large-scale patterns in the CMB appear unexpectedly correlated across billions of light-years, defies standard predictions. Some researchers argue it could hint at flaws in our understanding of the Big Bang, while others suspect mere observational artifacts, but either way, it forces us to question whether we're seeing the whole picture. The anomaly gets its dramatic name from the way these unexpected alignments seem to trace a particular direction through space, almost as if the universe has a preferred axis. In a cosmos that's supposed to be isotropic, looking the same in all directions, such a directional preference shouldn't exist. Imagine tossing confetti into the air, only to watch it arrange itself into perfect parallel lines instead of scattering randomly. That's the level of statistical peculiarity we're dealing with when examining the CMB's quadrupole and octupole moments, large-scale fluctuations that appear suspiciously aligned with our solar system's plane. Possible explanations range from the mundane to the revolutionary. On the conservative end, some scientists propose foreground contamination, galactic dust or other local interference mimicking patterns in the primordial light. Others suggest subtle biases in how we process CMB data, like the way researchers clean maps to remove the Milky Way's emissions might accidentally introduce artifacts. But the more provocative theories, these alignments might be evidence of a pre-Big Bang structure imprinting itself on our universe, or even signs that space isn't uniformly shaped as we assume. One radical hypothesis suggests the axis of evil could mark where our universe collided with another bubble universe during inflation. What makes this debate so electrifying is how it exposes science in action. The CMB is often treated as gospel truth, the gold standard of cosmology, but here it's raising questions we can't yet answer. Whether the axis of evil eventually gets explained as a measurement quirk or a crack in current theories, its existence reminds us that even our best cosmic maps might still be missing whole chapters of the universe's story. For now, this mysterious alignment stands as a cosmic Rorschach test. Some see shadows of new physics, others see noise, and the truth remains just out of reach. The cosmic microwave background doesn't just map ordinary matter. It exposes the invisible hand of dark matter sculpting the universe from its earliest moments. Those subtle temperature variations we've been exploring, they're actually a cosmic tug of war between visible particles and their mysterious, unseen counterparts. While normal matter interacted with light, creating pressure that resisted gravitational collapse, dark matter, completely indifferent to photons, was free to clump together under its own weight. This silent partnership set the stage for everything that followed. Think of it like building a city where only some workers can be seen. The visible construction crew, representing ordinary matter, has to navigate around cranes and scaffolding, slowing their progress. But an invisible team moves freely, assembling the structural framework long before bricks are laid. That's precisely what dark matter did in the early universe. Its gravity created deep wells that trapped normal matter once it cooled enough to fall in, like rainwater collecting in pre-carved riverbeds. The CMB captures this delicate dance in exquisite detail. The way slightly warmer spots correspond to regions where both dark and normal matter began gathering, while cooler patches mark the future homes of vast cosmic voids. What's groundbreaking is how precisely the CMB measures dark matter's fingerprint. By analyzing the statistical distribution of those temperature fluctuations, scientists can calculate exactly how much invisible mass must have been present to produce the observed patterns. The numbers are staggering. Dark matter outweighs normal matter by about 5 to 1. Without its gravitational influence, the slight overdensities in the early universe would have been far too weak to form galaxies within the age of the cosmos. Those microwave photons are essentially cosmic X-ray film, revealing the skeleton beneath the universe's visible flesh. Here's where it gets even more fascinating. Different dark matter candidates, whether WIMP, actions, or other theoretical particles, would have produced distinct signatures in the CMB's fluctuation patterns. The fact that the observed data matches cold dark matter models so precisely is perhaps our strongest evidence that this enigmatic substance exists at all. It's like solving a murder mystery by studying the shadow the killer left on a wall. We may not see the culprit directly, but its imprint tells us everything about its size, shape, and behavior. Yet the story doesn't end there. The CMB also reveals how dark matter shaped the universe's large-scale structure over time. Those initial gravitational wells determined where galaxies would eventually bloom, creating the vast cosmic web we observe today. By combining microwave background data with modern galaxy surveys, astronomers can literally watch dark matter's predictions unfold across billions of years, a celestial prophecy written in microwaves and fulfilled in starlight. This invisible architect continues influencing the CMB even now. As photons travel toward us, their paths bend slightly when passing through massive dark matter concentrations, an effect called gravitational lensing. Modern telescopes can detect these subtle distortions, allowing us to map dark matter's distribution in 3 dimensions. It's as if the universe left us not just a baby picture, but a full holographic record of its hidden half. What makes this evidence so compelling is its independence from other dark matter detection methods. While particle colliders and underground experiments search for direct interactions, and galaxy rotation curves measure local gravitational effects, the CMB provides a global snapshot from a time before stars complicated the picture. Together, these approaches form an irrefutable case dark matter isn't just a convenient explanation for modern astronomical puzzles. Its gravitational signature is literally baked into the oldest light in existence, proving it shaped the universe from day one. The cosmic microwave background does more than reveal the universe's infancy, it whispers secrets about its ultimate fate. Hidden within those microwave patterns is evidence of dark energy, the enigmatic force pushing galaxies apart faster than gravity can pull them together. While supernova first exposed this cosmic acceleration in the late 1990s, the CMB provides independent confirmation, painting a consistent picture of a universe dominated by something far stranger than matter or radiation. What makes the CMB such a powerful dark energy detector is its sensitivity to the universe's geometry and expansion history. Those temperature fluctuations act like cosmic rulers. Their apparent size on the sky reveals how space has stretched over billions of years. Here's the critical clue: the patterns appear slightly larger than they should if the universe contained only matter and dark matter. This subtle stretching matches predictions for an accelerating expansion, as if some invisible energy were steadily flexing spacetime itself. The numbers tell a startling story. Combining CMB data with supernova measurements shows dark energy constitutes about 68% of the universe's total energy budget. Unlike matter, whose gravitational pull weakens as the cosmos expands, dark energy's repulsive effect appears constant, or may even strengthen over time. This behavior is encoded in the CMB's large-scale patterns, where the spacing between acoustic peaks reflects how quickly space was expanding when those photons first broke free. But the real magic lies in how these datasets complement each other. Supernova act like mile markers, showing how expansion has accelerated recently, while the CMB serves as a fossil record, revealing how dark energy's influence grew from a whisper in the early universe to a shout today. Together, they form a cosmic before and after snapshot, proving acceleration isn't some local fluke. It's baked into the fabric of reality. What's particularly elegant is how the CMB measures dark energy indirectly. By precisely mapping the universe's flatness, a result of inflation's rapid stretching, it sets a critical benchmark. The total mass energy density must equal a specific value to maintain that flatness. When astronomers add up all ordinary matter, dark matter, and radiation, they find only 32% of the required amount, the missing 68%. That's dark energy's calling card, a vacancy in the cosmic ledger that can't be filled by anything else. Yet mysteries remain. The simplest dark energy model, Einstein's cosmological constant, fits the data beautifully, but we've no idea why it has the specific value it does. Some theories suggest dark energy might vary over time or interact with dark matter, subtly altering the CMB's fluctuation patterns. Future ultra-precise polarization measurements could catch these deviations, potentially revealing whether we're witnessing the birth of a new physics or just the first hints of a deeper cosmic mystery. For now, the CMB stands as our most robust evidence that dark energy isn't just mathematical sleight of hand, it's as real as the ancient light carrying its signature. Those microwave photons began their journey when the universe was 1,000 times smaller, unaware they'd one day testify to forces that would tear apart the very structures they helped create. In their faint glow, we read not just our origin story, but our destiny, a universe expanding faster every moment, driven by something we're only beginning to comprehend. Long before the first stars flickered to life, the universe was filled with a symphony of sound waves rippling through the searing plasma of creation. These primordial vibrations, called Baryon acoustic oscillations, left permanent scars in the cosmic microwave background, creating a celestial ruler that astronomers now use to measure the vast expanses of space. Imagine dropping a pebble into a pond, except the pond is a superheated soup of particles, and the ripples freeze in place for eternity. That's essentially what happened during the universe's first 400,000 years, leaving behind a fossilized echo that we can still decode today. Here's how this cosmic recording works. In the early universe's dense plasma, photons and baryons, particles like protons and neutrons, were locked in a violent tug of war. Photons exerted outward pressure like an intense wind, while gravity tried to pull matter inward. This created standing waves where regions of higher and lower density alternated in a regular pattern, much like musical notes vibrating in an instrument. When the universe cooled enough for atoms to form, photons broke free, and those pressure waves instantly froze in place, imprinting their signature onto the CMB like fingerprints in cooling glass. The scale of these oscillations is staggering, about 500 million light-years from peak to peak, a distance so vast it dwarfs entire galaxy clusters. Yet this precise spacing serves as a universal yardstick, because we know exactly how large these sound waves were when they fossilized. Any deviation in their apparent size today reveals how much the universe has stretched over billions of years. It's like finding a grid of perfectly spaced city blocks where the buildings have drifted apart. By measuring their current separation, we can calculate exactly how much the ground has expanded beneath them. What makes these sound wave fossils so revolutionary is their immunity to cosmic evolution. Unlike stars that burn out or galaxies that collide, these imprints remain pristine, allowing astronomers to compare ancient CMB maps with modern galaxy surveys. The result, a three-dimensional cosmic distance ladder confirming the universe's expansion with unprecedented precision. When combined with supernova and redshift data, these oscillations provide airtight evidence for dark energy's accelerating push, proving space isn't just growing, it's stretching faster every moment. But the real magic lies in the details. The way these sound waves' harmonics appear slightly dampened reveals the ordinary matter content of the early universe. Their subtle asymmetry hints at dark matter's gravitational influence, while their polarization patterns expose the exact moment when the first stars reignited the cosmic dawn. This isn't just a frozen sound wave, it's a multi-layered time capsule, each vibration tuned to tell a different chapter of the universe's story. Future telescopes aim to map millions of galaxies using these oscillations as guideposts, creating the most detailed expansion timeline yet. As we listen deeper into this cosmic static, we're not just hearing echoes of the past, we're decoding the very heartbeat of the universe, a rhythm set in motion when everything began. The cosmic microwave background isn't just ancient light. It's a portal to a time before time as we know it existed. When we capture those faint microwave photons with our telescopes, we're glimpsing the universe as it appeared a mere 380,000 years after the Big Bang, before a single star had ignited or any galaxy had taken shape. This makes the CMB the ultimate time capsule, preserving conditions from an era so distant that the very concept of years barely applies. Picture an infant universe still glowing from the violence of its birth, a dense, opaque sea of plasma so hot that atoms couldn't form. Electrons and protons raced about like frantic fireflies, constantly scattering photons in a blinding plasma fog. Then, in what cosmologists call recombination, the expanding cosmos finally cooled enough for electrons to combine with nuclei, creating the first neutral atoms. Suddenly, after hundreds of millennia of chaos, light could travel freely for the first time. Those newly liberated photons, the ones we now detect as the CMB, begin their 13-billion-year journey toward our telescopes, carrying with them an unaltered snapshot of that pivotal moment. What makes this time capsule so extraordinary is its purity. Unlike starlight filtered through generations of dust or distorted by gravitational lenses, these primordial photons come to us directly from the universe's surface of last scattering the final moment they interacted with matter. It's like receiving a letter sealed at the moment of writing, its contents untouched by the centuries between sending and delivery. The patterns we see in that microwave glow, those subtle temperature variations, are literally the original quantum fluctuations from the universe's first microseconds, stretched to cosmic scales by inflation and preserved in perfect deep freeze. This pristine quality allows scientists to perform what seems like magic, reconstructing the exact proportions of ordinary matter, dark matter, and radiation present when the universe was less than 0.003% of its current age. The CMB reveals that the early cosmos was about 4% ordinary atoms, 26% dark matter, and 70% radiation, a recipe that would eventually bake into the galaxies we see today. We can even detect the faint shadows of sound waves moving through that primordial plasma, their wavelengths acting as cosmic thermometers measuring the universe's temperature in its infancy. Perhaps most remarkably, this time capsule shows us what came before the things we consider ancient. The period before 380,000 years, the so-called Dark Ages, remains opaque to traditional telescopes. But by studying the CMB's polarization patterns and subtle distortions from gravitational lensing, researchers are beginning to peer even further back, potentially uncovering clues about inflation's first moments. It's as if we've discovered a family photo album where the earliest picture shows a teenager, but by studying the details in that image, we can infer what the baby must have looked like. This window into cosmic prehistory changes our perspective on everything. Those faint microwaves remind us that the grand galaxies and glittering star clusters we admire through telescopes were once nothing more than microscopic density variations in a searing plasma sea. The universe we know, with its black holes, supernova, and spiral galaxies, is just the evolved version of that simpler, hotter reality captured in the CMB's glow. Every structure owes its existence to those initial conditions, frozen in light when the cosmos took its first clear breath. As technology advances, we're extracting ever more information from this cosmic time capsule. Future observatories may uncover gravitational wave imprints from inflation or detect subtle spectral distortions revealing energy releases in the universe's first seconds. Each new discovery adds another page to what is already the most extraordinary history book imaginable, one written not in ink but in the oldest light the universe ever produced. Among the cosmic microwave background's near-perfect uniformity lies a chilling anomaly, the cold spot, a region of space so mysteriously frigid that it defies conventional explanations. Stretching nearly 2 billion light-years across, this patch of the CMB is significantly colder than its surroundings, as if someone left a cosmic freezer door ajar in the primordial glow. While most temperature variations in the microwave background are tiny fractions of a degree, the cold spot stands out like a frostbitten thumb, sparking debates among cosmologists about whether it's a statistical fluke, a glimpse of exotic physics, or even a bruise from a collision with another universe. One leading theory suggests the cold spot might be a cosmic void, a vast, mostly empty region of space where matter is unusually sparse. In such a void, photons from the CMB could lose energy as they travel through it, an effect known as the integrated Sachs-Wolf effect. Imagine rolling a marble up a hill that's slowly sinking beneath it. Even if the marble maintains its speed, it loses potential energy. Similarly, as light traverses a growing void, the expansion of space saps its energy, making the region appear cooler. Some surveys have indeed found an unusually large underdensity of galaxies in the cold spot's direction, but the scale required to explain the temperature drop would make it the largest void ever discovered, so colossal that it challenges our understanding of how structure forms in the universe. Then there's the far more speculative idea. The cold spot could be evidence of a cosmic collision with a parallel universe. According to certain multiverse theories, our universe might have bumped into another bubble during its early inflationary phase, leaving behind a kind of gravitational bruise in the CMB. While this hypothesis grabs headlines, most scientists remain skeptical, as no direct evidence supports it. But the mere possibility highlights how seriously researchers take this anomaly. When standard cosmology struggles to explain something, even fringe ideas get a hearing. What makes the cold spot so compelling is how it tests the limits of our cosmic models. If it's just a rare statistical fluctuation, it's a fluke so improbable that it should occur only once in every few hundred universes. If it's a void, it's far larger than simulations predict should exist. And if it's something else entirely, well, that could rewrite physics textbooks. Future galaxy surveys and high-resolution CMB measurements might finally crack the case, but for now, this icy enigma remains one of cosmology's most tantalizing unsolved puzzles, a cold splash of mystery in the universe's oldest light. The cosmic microwave background's eerie uniformity, that near-perfect sameness in temperature across billions of light-years, poses one of cosmology's greatest puzzles. How could regions so distant they've never been in causal contact share such identical conditions? The answer lies in a theory so radical it reshaped our understanding of the universe's first moments: cosmic inflation. Picture this: in the tiniest fraction of a second after the Big Bang, space itself underwent a growth spurt so violent it would make today's expanding universe seem sluggish by comparison. The entire observable cosmos ballooned from smaller than a proton to about the size of a grapefruit in less than a trillionth of a trillionth of a trillionth of a second. This exponential expansion wasn't just fast, it was faster than light itself. While Einstein's relativity forbids objects from moving through space faster than light, inflation exploits a cosmic loophole. Space can stretch at any speed. As the universe inflated, any initial irregularities got stretched so thin they became negligible, leaving behind the smooth thermal canvas we see in the CMB. It's like zooming in on a crumpled sheet of paper until the wrinkles disappear. Inflation ironed out the cosmic wrinkles, leaving only quantum-scale fluctuations imprinted as those 1 part in 100,000 temperature variations. But inflation does more than explain smoothness. It's the ultimate cosmic alchemist, turning microscopic quantum jitters into galaxy seeding structures. During inflation's frantic expansion, tiny quantum fluctuations got magnified to astronomical scales, becoming the density variations that later grew into galaxies and clusters. The CMB's slight temperature differences are essentially these stretched quantum imprints, frozen in time when inflation abruptly ended and the universe settled into a more sedate expansion. Without this process, the cosmos might have remained featureless: no stars, no planets, just a vast, boring sea of particles. Evidence for inflation goes beyond theoretical elegance. The theory predicted 3 specific traits found in the CMB. A flat universe, scale invariant fluctuations, meaning the pattern looks similar at any magnification, and a particular ratio of temperature variations at different angular scales. Satellite missions like Planck have confirmed these predictions with stunning precision, so precise, in fact, that inflation has become the gold standard for explaining the universe's earliest moments. Yet mysteries linger. Was inflation driven by some exotic field called the inflaton? And why did it start or stop? Some models suggest inflation might be eternal, with our universe just one bubble in a frothing multiverse. Others speculate about pre-inflationary physics that could leave subtle signatures in the CMB's polarization patterns. Future ultra-sensitive telescopes might detect these fingerprints, potentially revealing what, if anything, came before the Big Bang. What makes inflation's connection to the CMB so profound is how it bridges the quantum and cosmic realms. Those faint microwave patterns are quantum mechanics writ large, a microscopic phenomenon inflated to universal proportions. Every galaxy, every star, every atom in your body owes its existence to this brief but spectacular phase when the universe rewrote the rules of reality. The CMB doesn't just record inflation's aftermath, it's the ultimate replay of the moment space itself learned how to explode. That faint cosmic microwave background we've been exploring isn't just ancient, it represents the universe's very first photograph, taken the moment it became transparent to light. Up until that point, roughly 380,000 years after the Big Bang, the cosmos was a searing, opaque fog, a roiling plasma soup so dense that photons couldn't travel more than a fraction of an inch before colliding with free electrons. Light was trapped, bouncing endlessly like sunlight through a thundercloud. Then, in a cosmic event known as recombination, the expanding universe finally cooled below 3,000 degrees Kelvin, allowing electrons and protons to combine into neutral hydrogen atoms for the first time. This transformation was as sudden as it was profound. Suddenly, photons that had been imprisoned in the plasma for millennia found themselves free to stream through space unimpeded. That instantaneous release is what we now detect as the CMB, literally the first light that ever traveled freely through the universe. It's as if someone flicked on a cosmic light switch, ending the so-called dark ages before stars existed. These liberated photons have been journeying ever since, their wavelengths stretching with the expansion of space into the microwaves we observe today. What makes this moment so extraordinary is how perfectly it's preserved in the CMB's properties. Unlike starlight filtered through gas clouds or distorted by galaxies, these photons carry an unaltered snapshot of conditions at that exact instant when the universe transitioned from opaque to transparent. Their uniformity tells us how smooth matter distribution was at recombination, while the tiny fluctuations reveal where gravity was already beginning to pull matter into the seeds of future galaxies. But here's what's truly mind-bending. We're not just seeing light from that era, we're seeing the actual surface where it last scattered. Because the universe became transparent everywhere simultaneously, the CMB forms a spherical shell around us at a distance of about 46 billion light-years, the farthest we can possibly observe in any direction. Every point in the sky represents a different location on this surface of last scattering, like a cosmic version of standing inside a glowing lantern where every inner surface shines with trapped firelight from long ago. This first light also carries forensic evidence about the universe's chemical infancy. The precise temperature at which recombination occurred depended on the ratio of protons to photons, a number so finely tuned that altering it slightly would have prevented atoms from forming when they did. The fact that hydrogen and helium nuclei captured electrons at just the right moment allowed the universe to transition from plasma to gas, setting the stage for everything that followed. Yet for all its significance, this flash of first light wasn't bright as we'd imagine. Not a dazzling burst, but a warm glow shifting from yellow to red as space expanded, eventually fading into invisibility before redshifting further into microwaves. Early humans might have glimpsed its last visible remnants as a dim, uniform reddish hue in the sky now long vanished due to cosmic expansion. We're incredibly fortunate to still detect its microwave echo at all, as future civilizations billions of years from now might find it redshifted beyond recognition into faint radio waves. This moment of first light wasn't just a passive transition, it was the universe's debut as a recognizable place, the instant it became capable of casting shadows and hosting structures. Every photon since, every glimmer of starlight, every flash from distant quasars, has simply been filling in details on a canvas first painted by that primordial glow. When we map the CMB, we're not just studying ancient history, we're witnessing the universe's very first act of self-revelation when it finally opened its eyes and began to shine. For decades, cosmologists were locked in a heated battle over the very nature of our universe, Was it eternal and unchanging, or did it have a definitive explosive beginning? The discovery of the cosmic microwave background didn't just provide new data, it decisively ended this grand scientific debate by delivering irrefutable evidence that shattered the once popular steady-state theory. The steady-state model, championed by astronomers like Fred Hoyle in the mid-20th century, proposed an elegant but ultimately flawed vision. An infinite universe with no beginning or end, where matter continuously appeared to fill the gaps as space expanded. No messy singularity, no primordial fireworks, just an eternal cosmic ballet where the overall density remained constant despite the stretching of space. At first glance, it avoided the philosophical quandaries of a creation event while matching many observations of galactic redshifts. But the CMB struck this theory at its core. Steady state predicted no universal background radiation. Why would there be a uniform thermal glow if the universe had always existed in roughly the same state? When Penzias and Wilson accidentally detected that telltale microwave hiss emanating from every direction, it perfectly matched the Big Bang's prediction of a cooling fireball remnant. Here was radiation left over from a specific, finite moment when the entire universe transitioned from opaque to transparent, a relic impossible to explain in an eternal cosmos. The knockout blow came when scientists measured the CMB's spectrum. It followed what physicists call a perfect blackbody curve, the distinctive thermal signature of an object in thermodynamic equilibrium. This precise energy distribution could only arise from an era when the entire universe was a searing, dense plasma, not from any known process in a steady-state scenario. Even the theory's proponents struggled to explain how starlight scattered by hypothetical iron whiskers in space could replicate such a flawless thermal profile. What made this paradigm shift so remarkable was how completely the CMB resolved multiple lines of evidence at once. Its temperature, isotropy, and spectrum together painted an incontrovertible picture of a hot, dense origin. Meanwhile, steady state required increasingly convoluted explanations for each new observation, like a crumbling mansion propped up with makeshift supports. By the 1970s, the combined weight of CMB data, helium abundance measurements, and galaxy evolution studies left the theory with virtually no scientific supporters. Yet this historic clash still offers profound lessons about how science self-corrects. The steady-state model wasn't foolish. It was a serious attempt to explain the cosmos with the data available at the time. Its eventual overthrow demonstrates science's willingness to abandon even elegant theories when evidence demands it. The CMB didn't just settle a debate, it showed how nature's verdict, written in microwave light, can rewrite humanity's most cherished cosmic narratives overnight. Those tiny temperature variations in the cosmic microwave background, the ones that seeded every galaxy and star, weren't just random blips. They were quantum mechanics writ large, microscopic tremors from the universe's first moments stretched to cosmic proportions by inflation's explosive expansion. Picture the subatomic realm as a frothing sea where particles wink in and out of existence, creating fleeting ripples of energy. In the ordinary world, these quantum jitters are imperceptibly small, vanishing almost instantly. But in the first trillionth of a second after the Big Bang, inflation's runaway expansion grabbed these nanoscopic fluctuations and yanked them across the entire cosmos like taffy pulled to infinity. This cosmic magnification process transformed quantum noise into the architectural blueprints for reality. Regions that started as slightly denser due to these quantum ripples gained extra gravitational pull, attracting more matter over billions of years. The result, the vast cosmic web we see today, with its glittering galaxies and yawning voids, all tracing back to those initial quantum seeds. It's as if the universe took a handful of subatomic confetti and inflated it into a galaxy-spanning mosaic. What's astonishing is the precision of this scaling. The CMB's fluctuations follow a pattern called scale invariance, meaning the distribution of hot and cold spots looks similar whether you examine large swaths of the sky or tiny patches. This fingerprint matches exactly what inflation predicts: quantum fluctuations blown up to every conceivable size simultaneously. It's like blowing up a balloon with a fractal pattern. No matter how much you inflate it, the design retains its essential character. These quantum origins also solve one of cosmology's deepest puzzles: where structure came from in the first place. Without those initial irregularities, gravity would have had nothing to work with, leaving the universe a perfectly smooth and perfectly boring sea of particles. Instead, the microscopic became macroscopic, the quantum became classical, and the seeds of galaxies were sown in the universe's fiery infancy. Yet the story doesn't stop there. Different models of inflation predict subtle variations in how these quantum fluctuations get stretched. Some theories suggest the fluctuations might have preferred directions or slight deviations from perfect scale invariance. By scrutinizing the CMB's patterns with ever greater precision, scientists are effectively performing quantum archaeology, using the universe's largest structures to probe physics at the smallest conceivable scales. This quantum-to-cosmic connection is perhaps the most breathtaking aspect of the CMB. Every galaxy, every star, every planet owes its existence to uncertainty principles and vacuum fluctuations operating in a realm a billion times smaller than an atom. The universe didn't just emerge from a hot, dense state, it crystallized around quantum randomness, transforming what was once the domain of theoretical physics into the very foundation of reality. Those microwave photons aren't just ancient light, they're the universe's first quantum ledger, recording the moment the infinitesimal became eternal. Future telescopes probing even finer details of the CMB's polarization may uncover deeper layers of this quantum origin story, potentially revealing signatures of quantum gravity or other phenomena operating at energies far beyond what particle colliders can reach. For now, the message is clear. The quantum and the cosmic aren't separate domains, they're chapters in a single, continuous saga written in microwaves across the sky. The cosmic microwave background has become the ultimate arbiter in one of cosmology's most heated debates: the Hubble tension, a stubborn discrepancy in how fast the universe is expanding. On one side, meticulous measurements of the CMB suggest an expansion rate of about 67 kilometers per second per megaparsec. On the other, observations of nearby stars and supernova consistently land near 73. At first glance, this 6-kilometer difference might seem trivial, but in the ultra-precise world of modern astrophysics, it's a glaring inconsistency that could shake the foundations of our understanding. This isn't just about numbers, it's a cosmic detective story with high stakes. The CMB's estimate comes from reverse engineering the universe's expansion history using the microwave background's fluctuation patterns as a time capsule. By factoring in dark energy, dark matter, and the universe's geometry, scientists can calculate how quickly space must have stretched to produce the structures we see today. It's like reconstructing a car's speed by examining skid marks and road conditions. Meanwhile, local measurements use pulsating stars called Cepheids and Type Ia supernova as standard candles of objects with known brightness that reveal distances. These observations act like cosmic radar guns, clocking the universe's current expansion speed directly. The problem: these two methods should agree, yet they stubbornly don't. And with each new generation of telescopes, from Hubble to JWST, the gap refuses to close. Some researchers have scrutinized every possible source of error: instrument miscalibrations, dust obscuration, even the peculiar motions of galaxies, but no mundane explanation fits. This leaves a tantalizing possibility. The discrepancy might be evidence of new physics, something beyond our standard cosmological model. One radical idea suggests dark energy isn't constant but evolves over time, subtly altering the expansion rate in ways the CMB alone wouldn't capture. Others propose exotic neutrino properties, or even that dark matter interacts with itself in ways we haven't accounted for. Then there's the wild card early dark energy, a hypothetical force that flared up briefly in the universe's infancy, skewing the CMB's snapshot of expansion while leaving local measurements untouched. What makes this puzzle so electrifying is how it forces scientists to question their most cherished assumptions. The CMB has been our North Star for decades, its data so precise it's often treated as gospel. Yet here it is, locked in a standoff with direct observations, refusing to yield. Whether the resolution comes from refined measurements or a revolutionary theory, one thing is certain. The Hubble tension isn't just a technical glitch, it's a cosmic breadcrumb, possibly leading us to discoveries that could redefine the universe's story. Right now, the cosmic microwave background glows faintly in every direction, a remnant echo from the dawn of time, but this ancient light won't last forever. As the universe accelerates its expansion, those primordial photons will stretch into ever longer wavelengths, redshifting beyond detection like a distant ship's horn fading into silence. Scientists predict that in roughly 150 billion years, the CMB will have cooled to such extreme lows that its signal will drown completely in the background noise of the cosmos. Future civilizations may gaze into deep space and find no trace of the universe's birth certificate, their skies stripped of this critical clue to cosmic origins. This gradual disappearance isn't just about temperature, it's a fundamental change in how the universe reveals itself. Today, the CMB gives us a direct line to conditions just 380,000 years after the Big Bang. But as space stretches, those microwave photons will shift first into radio waves, then into undetectably low-frequency ripples. It's like watching a piano string slacken over millennia until they no longer vibrate audibly. The very expansion that preserved this light for us now works to erase it, stretching the photons so thin they effectively vanish from observational reach. What makes this impending loss so profound is the knowledge it takes with it. Without the CMB's crisp snapshot of the early universe, future astronomers would lack our most definitive evidence for the Big Bang, cosmic inflation, and dark matter's role in structure formation. They might puzzle over why galaxies are arranged in vast webs or struggle to measure the universe's curvature without this cosmic yardstick. Imagine trying to reconstruct your family tree after someone burned all the birth records. That's the challenge post-CMB civilizations could face. Yet even as the primordial glow fades, its legacy persists. The structures it helped seed, galaxies, clusters, and superclusters, will endure far longer, carrying encoded clues about their origins. Advanced civilizations might decipher cosmic history from Baryon acoustic oscillations frozen in galaxy distributions or study reionizations, subtle effects on distant quasars. But these methods would be indirect, like reconstructing a fire from its smoke trails long after the flames have died. This slow cosmic forgetting raises existential questions about how eras of the universe leave evidence behind. We're privileged to exist during a brief window where the CMB remains detectable, a golden age for cosmology when the universe's earliest light still reaches us clearly. Future epochs may know only darkness between the stars, unaware that their expanding home once burned bright with the afterglow of creation. The cosmic microwave background may be our universe's oldest light, but some researchers wonder if it holds cryptic messages from realities beyond our own. Among the most tantalizing possibilities is that certain anomalies in the CMB, like the enigmatic cold spot, could be cosmic bruises from collisions with other bubble universes in a vast multiverse. Imagine our universe as one soap bubble floating in a frothy sea of others, each with its own distinct physics and dimensions. If another bubble even grazed ours during inflation's furious expansion, the impact could have left gravitational scars imprinted on the CMB like fingerprints on glass. This radical idea stems from eternal inflation theory, which suggests our universe is just one pocket in an endlessly inflating megaverse. As neighboring bubble universes nucleate and expand, their boundaries might occasionally collide, transferring energy in ways that distort the cosmic microwave background. The cold spot, with its unusually frigid temperature spanning nearly 2 billion light-years, fits eerily well with simulations of such collisions. Computer models show these impacts would create distinctive circular patterns of temperature variation, slightly cooler at the center with a warmer ring surrounding them, matching the cold spot's observed structure closer than any void-based explanation. Critics counter that such theories venture dangerously close to untestable speculation. Without independent evidence for other universes, linking CMB anomalies to multiverse collisions risks becoming a just-so story, an appealing narrative with no falsifiable predictions. But proponents argue that careful statistical analysis of the CMB's full sky patterns could reveal telltale signatures. For instance, a true bubble collision should produce not just one anomaly, but multiple concentric rings of temperature variation at specific angular scales. It might also leave a distinct polarization pattern in the surrounding microwaves, like ripples spreading from a pebble dropped in a pond. What makes this speculation so compelling is how it transforms the CMB from a relic into a potential Rosetta Stone for realms beyond our cosmic horizon. If confirmed, even one multiverse collision imprint would revolutionize our understanding of reality, proving that our universe isn't just expanding, it's bumping up against neighbors we can never directly see. Future deep-field CMB surveys with next-generation telescopes could hunt for these ghostly fingerprints, scanning for statistical anomalies that might betray contact with other dimensions. Yet the cold spot isn't the only CMB feature fueling multiverse theories. The large-scale hemispheric asymmetry, where one half of the sky shows slightly stronger temperature fluctuations than the other, might indicate our universe inherited lopsided conditions from a pre-inflationary multiverse environment. Some models even suggest that quantum entanglement between our universe and a sibling could leave subtle correlations in the microwave background's fluctuation patterns, like identical twins sharing mannerisms despite growing up apart. This intersection of hard data and bold theorizing showcases cosmology at its most thrilling. The CMB began as a cosmic afterthought, static in a radio antenna, but now serves as a canvas for our most profound questions about existence. Whether these anomalies ultimately trace to parallel universes or more mundane astrophysics, their investigation pushes the boundaries of how we interrogate reality. Every unexplained ripple in that ancient light whispers the same tantalizing question: are we reading the diary of a single universe or just one page in an infinite library? Even as the cosmic microwave background glows with near-perfect uniformity across the sky, it holds one glaring inconsistency: the dipole anisotropy, a lopsided pattern caused by our solar system's motion through space. This Doppler-shifted hotspot, where microwaves appear slightly warmer in the direction we're moving and cooler behind us, should theoretically align perfectly with the observed motions of nearby galaxy clusters. Yet something's off, the numbers don't match. Our measured velocity through the CMB suggests we're hurtling at roughly 600 kilometers per second, but galaxy surveys reveal large-scale flows tugging us in slightly different directions. This discrepancy isn't just a minor calibration error. It hints at gravitational forces so vast they might trace to structures beyond our observable horizon. The mystery deepens when you consider what should be causing this motion. On large scales, the universe's mass distribution ought to be uniform enough that galaxies and galaxy clusters move in harmony with the CMB's reference frame. Instead, we're seeing evidence of a dark flow, a collective drift of galaxy clusters that extends farther than current models can comfortably explain. Some researchers suggest this might be the gravitational pull of superclusters so enormous they lie just outside our cosmological vision. their combined mass subtly redirecting entire galaxy clusters like invisible rivers steering ships. Others propose even more radical ideas, that these flows could betray the influence of a neighboring universe's gravity leaking through the multiverse foam, though such claims remain highly speculative. What makes this mismatch so puzzling is its scale. The dipole anomaly isn't confined to our local galactic neighborhood. It persists across surveys mapping thousands of galaxy clusters spanning billions of light years. If conventional gravity alone were at work, these distant clusters shouldn't share our peculiar motion. Yet observations from X-ray telescopes and the kinetic Sunyaev-Zeldovich effect consistently show clusters moving in ways that defy expectations, as if some unseen hand is nudging the cosmic chessboard. This isn't just academic curiosity. The dipole discrepancy could rewrite our understanding of the universe's largest structures. Normally, we assume that matter distribution becomes smooth on scales beyond a few 100 million light-years, but these flows suggest there might still be density variations enormous enough to exert gravitational influence across unimaginable distances. Future galaxy surveys and precision CMB measurements from projects like the upcoming CMB Stage 4 observatory aim to map these motions in unprecedented detail, potentially revealing whether we're dealing with known physics stretched to extremes or something entirely new. For now, the misaligned dipole stands as a humbling reminder. Even our most precise cosmic map still holds regions labeled "Here be dragons." Whether the answer lies in undiscovered superstructures, modifications to gravity, or phenomena beyond current theories, one thing is clear. The universe's oldest light still has secrets to share, and some of them might be written in the blank spaces between the notes we thought we understood. Among the subtle temperature variations of the cosmic microwave background, some researchers claim to have found something extraordinary: concentric circular patterns etched into the ancient light like ripples from a stone tossed into a pond. These claimed anomalies, first identified in 2010 by a team analyzing WMAP satellite data, appear as faint rings of slightly warmer and cooler temperatures spanning vast swaths of the CMB sky. To their proponents, these circles aren't random fluctuations but cosmic bullet holes, evidence of violent collisions between our universe and others in a multiverse, or perhaps even echoes from universes that existed before our own Big Bang. The theory behind these circles taps into radical cosmological models like conformal cyclic cosmology, proposed by physicist Roger Penrose. His vision suggests an endless cycle of universes where each eon's death becomes the next birth through an elaborate recycling of spacetime geometry. In this framework, supermassive black holes from a previous universe might leave gravitational imprints on the next, manifesting as concentric temperature variations in the CMB. Similarly, bubble universe collisions in eternal inflation scenarios could produce circular bruising where two expanding spacetime membranes briefly touched before rebounding apart. Mainstream cosmology, however, remains deeply skeptical. The primary criticism centers on statistics. The universe is so vast that even random temperature fluctuations will occasionally form what appear to be patterns when viewed with selective filtering techniques. When independent teams applied more rigorous statistical tests to the original circle claims, most found the patterns consistent with chance alignments in Gaussian noise. The Planck satellite's higher resolution data later failed to conclusively confirm the anomalies at predicted scales, dealing another blow to the hypothesis. Yet the debate reveals something profound about how science grapples with extraordinary claims. The circle's hypothesis didn't emerge from nowhere. It was a legitimate attempt to explain genuine oddities in early CMB maps, like the unexpected scarcity of large-scale fluctuations compared to standard inflationary predictions. Even as most researchers attribute these features to instrumental noise or foreground contamination, the investigation pushed cosmologists to develop more sophisticated tools for distinguishing true anomalies from cosmic mirages. What makes this search so compelling is its stakes. If verified, concentric CMB patterns would revolutionize our understanding of reality, offering the first observational evidence for phenomena beyond our spacetime. Future high-precision polarization measurements from projects like the Simons Observatory could settle the debate, either revealing subtle gravitational wave imprints within the rings or confirming their statistical insignificance. Until then, these phantom circles serve as a reminder the universe's oldest light may still hold revelations we're only beginning to imagine. Buried within the cosmic microwave background's temperature fluctuations lies evidence of the universe's most elusive cosmic spectators, primordial neutrinos. These ghostly particles, so insubstantial that trillions pass through your body every second without a trace, once dominated the early universe in staggering numbers. The CMB preserves their faint fingerprints, not as direct signals but through subtle distortions in the ancient light's patterns. A cosmic game of connect the dots where missing pieces reveal invisible players. When the universe was just 1 second old, neutrinos outnumbered protons and electrons by over 1 billion to 1, flooding space like an invisible cosmic fog. Unlike ordinary matter, these particles barely interacted with anything streaming freely through the newborn cosmos at nearly light speed, but their sheer abundance gave them extraordinary influence. As the universe expanded, these relativistic particles shaped its growth rate, subtly tugging at spacetime like an unseen hand guiding a balloon's inflation. The CMB captures this influence in 2 remarkable ways: by altering the timing of when matter began clumping into galaxies, and by smearing the apparent size of temperature fluctuations in telltale ways. Here's where it gets fascinating. Neutrinos' near light speed motion created a unique drag effect on cosmic structure formation. Imagine trying to build sandcastles while waves keep washing over the beach. That's what these particles did to early matter density fluctuations. Their relentless movement smoothed out small-scale wrinkles in the matter distribution, effectively erasing galaxy seeds below a certain size. The CMB's fluctuation spectrum reflects this suppression, a statistical deficit of small hot and cold spots that precisely matches predictions for how primordial neutrinos should have sculpted the cosmos. Even more astonishing, the CMB allows us to count these ghostly particles. By analyzing the microwave background's detailed power spectrum, essentially the cosmic equivalent of a sound equalizer graph, scientists have confirmed the existence of exactly 3 neutrino families, aligning perfectly with particle physics discoveries made in Earth-bound accelerators. It's as if the universe left us 2 independent manuals, one written in particle collisions underground, the other in microwaves across the sky, and both tell the same story. But the revelations don't stop there. Modern CMB experiments are now sensitive enough to probe neutrinos' actual masses through their gravitational effects on light. As these particles slowed from relativistic speeds over cosmic time, their collective gravity began subtly warping the paths of CMB photons, an effect called gravitational lensing. By mapping these distortions, researchers have placed the tightest upper limits yet on neutrino masses, confirming they must be at least 500,000 times lighter than electrons. This neutrino fossil record holds even deeper puzzles. Some theories suggest additional, sterile neutrinos might exist, particles that interact only via gravity, which could leave distinctive imprints in the CMB's polarization patterns. Others propose that neutrino properties might help explain the universe's matter-antimatter asymmetry. Future ultra-precise CMB measurements could settle these debates, potentially uncovering physics beyond the standard model using nothing but ancient light and the faintest of cosmic whispers. What makes this detective story so compelling is how it connects quantum-scale physics with the grandest cosmic scales. Those nearly massless neutrinos, forged in the universe's first second, left scars visible 13 billion years later in the microwave sky. The CMB doesn't just show us where we came from, it preserves the signatures of particles we can barely detect today, offering a time capsule from an era when the cosmos was so dense and hot that even the most aloof particles played a starring role. As we refine our measurements, we're not just studying relics, we're reading the diary of the universe's most elusive inhabitants. The cosmic microwave background's near-perfect symmetry hides a puzzling lopsidedness, one that challenges our most fundamental assumptions about the universe's structure. While the CMB's temperature fluctuations appear remarkably uniform at first glance, closer inspection reveals a strange hemispheric imbalance. The northern celestial hemisphere shows slightly stronger temperature variations than the southern, as if someone took a cosmic paintbrush and added extra texture to just one half of the sky. This parity asymmetry, first spotted in WMAP data and later confirmed by Planck, defies the cosmological principle, the bedrock idea that the universe should look statistically identical in all directions when viewed on large enough scales. What makes this imbalance so perplexing is its scale. The asymmetry isn't confined to a small patch, it spans hemispheres billions of light-years across, far larger than any known astrophysical structure could explain. Standard inflationary models predict these fluctuations should be evenly distributed, like breadcrumbs scattered randomly across a table. Instead, we're seeing evidence that the early universe might have had a preferred direction, subtly breaking the rotational symmetry we've always taken for granted. Some researchers describe it as finding a fingerprint on what should be a perfectly smooth sphere, a mark suggesting the cosmos isn't as isotropic as we thought. Possible explanations range from the mundane to the revolutionary. On the conservative end, foreground contamination from our own Milky Way or subtle instrumental biases could mimic such patterns. Yet even after exhaustive cleaning of galactic dust and careful calibration, the signal persists. More provocative theories suggest this could be evidence of pre-inflationary physics, relic structures from whatever existed before the Big Bang that imprinted their asymmetry onto our nascent universe. Others propose modifications to inflation itself, where quantum fluctuations generated more pronounced wrinkles in one spatial direction than others. Then there's the truly mind-bending idea. The asymmetry might trace to the universe's topology, hinting that space itself could be shaped like an enormous twisted funnel on scales beyond our observable horizon. The implications ripple across cosmology. If this handedness proves real, it could force revisions to how we model inflation's quantum fluctuations or even our understanding of spacetime's fundamental symmetries. Future CMB experiments with enhanced polarization sensitivity might catch subtle correlations between temperature and polarization patterns that could distinguish between these theories. For now, the asymmetry stands as one of cosmology's great open questions, a silent challenge written in microwaves across half the sky, reminding us that the universe's oldest light still guards secrets we're only beginning to decipher. Those delicate wrinkles in the cosmic microwave background aren't just relics, they're the DNA of the universe, the genetic code that dictated how empty voids and glittering superclusters would one day arrange themselves into the largest structures we can observe. When you gaze at modern maps of the cosmic web, those breathtaking filaments of galaxies stretching across billions of light-years like strands of a spider's silk, you're actually seeing the amplified echo of those same microscopic fluctuations frozen into the CMB when the cosmos was 1,000 times smaller. The connection isn't poetic, it's mathematical, with computer simulations now able to trace an unbroken chain from those initial quantum seeds to the sprawling architecture of today's universe. Take one of those slightly warmer patches in the microwave background, a region where matter was a fraction of a percent denser than average. Over billions of years, that microscopic overdensity acted like a gravitational magnet, pulling in surrounding gas and dark matter. As more material collected, the gravitational pull intensified, accelerating the process in a runaway feedback loop. What began as a quantum blip smaller than an atom grew into a protogalactic cloud, then a young galaxy, and eventually the heart of a massive cluster anchoring intersecting filaments of the cosmic web. The cooler patches, those became today's vast voids, regions so empty they can span hundreds of millions of light years, their underdensity preserved like bubbles in rising dough. The precision of this growth is staggering. Modern cosmological simulations like Illustris TNG can literally input the CMB's fluctuation patterns as initial conditions, press play, and watch as virtual universes evolve with structures eerily similar to those mapped by galaxy surveys. It's like feeding a drop of pond water into a supercomputer and watching it accurately predict where every lily pad and fish will be decades later. The simulations reveal how dark matter, invisible but overwhelmingly influential, formed an invisible scaffold first, its gravity shaping the pathways along which ordinary matter later flowed. That's why the cosmic web looks frothy rather than clumpy. Dark matter's weak interactions allowed it to settle into delicate filaments, while regular matter piled up where those threads intersected. But here's where it gets even more fascinating. The CMB doesn't just explain the web's existence, it encodes the rules of its growth. The angular size of those acoustic oscillations in the microwave background directly corresponds to the spacing of filaments in today's cosmic web. That 500 million light-year rhythm, the Barrian acoustic oscillations we explored earlier, manifests as a slight excess of galaxy pairs separated by that exact distance. It's as if the universe stamped its fingerprint onto the distribution of matter, leaving a signature so clear we can still detect it 13 billion years later. Zoom out far enough and the resemblance becomes uncanny. The same fractal branching pattern seen in neurons, river deltas, and lightning bolts recurs in the cosmic web, not by chance, but because all these systems obey the same underlying physics of flow along optimal pathways. The difference is scale. Where lightning takes milliseconds to form, the cosmic web required billions of years, with gravity doing the work of electric potential. Those initial quantum fluctuations in the CMB set the template, but the universe's emergent complexity did the rest, transforming a near-uniform plasma into a labyrinth of light and shadow on scales that dwarf human imagination. Yet for all its grandeur, the cosmic web remains fragile. Recent observations show filaments thinner and more tenuous than predicted, their gas so diffuse it's barely detectable except by the way it distorts background light. This unexpected fragility hints at complexities in how energy from supermassive black holes and supernova might be heating intergalactic spaces, stirring the cosmic pot in ways simulations are still learning to model. The web isn't static. It's a dynamic, evolving entity with galaxies migrating along filaments like commuters on a vast interstellar highway system. What makes this connection between microwaves and galactic cities so profound is its universality. Every structure, from the smallest dwarf galaxy to the largest supercluster, owes its existence to those initial conditions captured in the CMB. The web's beauty lies not just in its scale, but in its democracy. Every patch of sky, no matter how empty it appears today, began with the same raw materials and physical laws. The diversity we see now emerged from identical origins, a reminder that cosmic evolution thrives on minute variations amplified by time. Those ancient photons don't just show us where we came from. They reveal the invisible thread stitching every galaxy, every star, every atom into a single, interconnected tapestry. Hidden within the cosmic microwave background's delicate temperature variations is a cosmic eraser at work, an effect so precise it selectively smoothed away the universe's smallest wrinkles while preserving its larger patterns. This phenomenon, known as silk damping, stems from a fierce tug of war between light and matter in the primordial plasma, leaving behind a telltale absence of ultra-tiny fluctuations that reveals volumes about the universe's earliest moments. Picture the infant cosmos as a superheated sea where photons and electrons endlessly collide, scattering like frenzied billiard balls. In such chaotic conditions, photons couldn't travel far before ricocheting off charged particles. a process creating relentless pressure that resisted gravity's attempts to compress matter into denser clumps. For the smallest density fluctuations, this photon pressure was catastrophic. Imagine trying to mold a sandcastle while waves crash over it every second. Any tiny structure gets washed away before it can stabilize. That's precisely what happened to quantum ripples smaller than about 10,000 light-years across. The photon's relentless scattering erased them entirely, leaving a distinct cutoff in the CMB's fluctuation spectrum. What makes silk damping so invaluable to cosmologists is how it acts like a cosmic spectrometer, revealing the exact moment when matter and radiation decoupled. The effect's damping scale, the specific size below which fluctuations vanish, depends critically on how long photons and electrons remained coupled. By measuring this cutoff with satellites like Planck, scientists can pinpoint the universe's density and expansion rate during recombination with astonishing precision. It's as if the early universe left us a ruler where the smallest markings were deliberately sanded off, telling us exactly how much friction existed between light and matter. But the story doesn't end there. Silk damping's fingerprints also expose the ordinary baryonic matter content of the early cosmos. Since photons interacted solely with charged particles, the damping depth reflects how many free electrons were available to scatter light. This allows researchers to calculate the baryon-to-photon ratio, a critical number determining everything from how quickly galaxies form to why the universe contains matter at all. The CMB's missing small-scale fluctuations are more than empty gaps. They're negative images of the particles that once filled space. Remarkably, this erasure of fine details also explains why the universe didn't fragment into countless microscopic black holes. Without silk damping's smoothing effect, quantum fluctuations at tiny scales might have grown uncontrollably, collapsing into primordial black holes that could dominate the cosmos today. Instead, the process acted like a cosmic blender, homogenizing the smallest irregularities while allowing larger structures to mature into galaxies and clusters. Modern cosmology exploits silk damping's subtle signals to probe beyond standard models. Some theories predict exotic particles like dark matter might have interacted with photons differently, altering the damping tail in detectable ways. Others suggest early dark energy or modified gravity could leave unique imprints on the missing fluctuations. As telescopes like the Simons Observatory analyze the CMB's damping scale with unprecedented precision, we're essentially conducting a forensic examination of the universe's first thermodynamic battle, a clash between light's desire to spread out and gravity's insistence to clump together. This vanishing act at small scales isn't a flaw in the cosmic blueprint, it's a masterstroke of balance. Just as an artist knows when to stop adding detail to avoid overwhelming a painting, silk damping ensured the early universe preserved only the most essential fluctuations. The result, a cosmos neither too smooth nor too chaotic, but perfectly primed to weave the grand tapestry of galaxies we admire today. Mapping the cosmic microwave background required more than just telescopes. It demanded instruments so sensitive they could detect temperature variations smaller than a millionth of a degree across the vast expanse of space. The quest to decode this ancient light launched a series of revolutionary space missions, each building on the last to peel back another layer of cosmic history. From the first rough sketches by COBE to Planck's exquisite high-definition portrait, these spacecraft transformed our understanding of the universe's origins while setting new standards for precision cosmology. The journey began with NAS, a Cosmic Background Explorer, or COBE, which launched in 1989. Imagine trying to measure the heat of a cup of coffee left to cool for 13 billion years. That was the challenge facing COBE's science team. Despite its modest resolution by today's standards, the satellite achieved something extraordinary. It confirmed the CMB's near-perfect blackbody spectrum with such precision that the data points lined up flawlessly with theoretical predictions. This wasn't just confirmation of the Big Bang, it was the first direct evidence that the early universe behaved like a thermalized plasma, exactly as physicists had hypothesized. COBE also produced the first all-sky map of the CMB's temperature variations, revealing those critical 1 part in 100,000 fluctuations that later missions would explore in detail. The mission's leaders, John Mather and George Smoot, earned Nobel Prizes for their work, but perhaps their greatest legacy was proving that the faint microwave whisper held decipherable secrets about cosmic infancy. A decade later, the Wilkinson Microwave Anisotropy Probe WMAP took the baton with 5 times COBE's resolution. Where its predecessor saw blurry patches, WMAP revealed intricate texture, like switching from a foggy bathroom mirror to high-definition glasses. This satellite didn't just map temperatures, it precisely measured the universe's age, composition, and geometry. Its data pinned down the cosmos' age to 13.7 billion years with unprecedented certainty, and revealed the shocking breakdown of its contents: 4% ordinary matter, 23% dark matter, and 73% dark energy. WMAP also captured the CMB's polarization for the first time, opening a new window into the universe's earliest moments. The probe's 9 years of observations became the gold standard for cosmology, but the best was yet to come. Enter the European Space Agency's Planck satellite, launched in 2009 as the most advanced CMB mapper ever conceived. Planck's instruments were so sensitive they could detect temperature differences equivalent to variations in a cup of microwaved coffee across the diameter of the Milky Way. Its resolution was 3 times sharper than WMAP's, allowing scientists to distinguish between competing theories of inflation and even spot potential anomalies like the controversial axis of evil. Planck's data refined the universe's expansion rate, tightened estimates of neutrino species, and produced the most detailed map of the cosmic web seeds ever created. But its crowning achievement was measuring the CMB's polarization with enough precision to glimpse the shadow of primordial gravitational waves, ripples in spacetime from inflation's first moments. These missions didn't just build better maps, they created a living timeline of cosmic precision. COBE showed us the CMB's broad strokes, WMAP filled in the paragraph details, and Planck revealed the individual brushstrokes. Together, they transformed cosmology from a field of speculation into a precision science, where theoretical predictions could be tested against exquisitely detailed observations. Future missions like the proposed CMB Stage 4 aim to push even further, potentially capturing the fingerprints of quantum gravity or uncovering evidence of other universes. What makes these spacecraft so extraordinary isn't just their technological prowess, it's how they turned philosophical questions into measurable data. Before COBE, the Big Bang was just one competing theory among many. After Planck, we hold baby pictures of the universe so sharp they reveal the gravitational scars of its first trillionth of a second. These missions didn't just observe the cosmos, they taught us to read it, transforming microwave static into the universe's most profound origin story. The cosmic microwave background isn't just another piece of the cosmological puzzle, it's the very foundation upon which our understanding of the universe rests. Those 30 astonishing facts we've explored together reveal why this ancient glow remains the single most important discovery in modern cosmology. From confirming the Big Bang's explosive birth to exposing the invisible scaffolding of dark matter, from timing the universe's expansion to unveiling its quantum origins, the CMB serves as both time capsule and oracle. Every photon that reaches our telescopes carries 13.8 billion years of history in its faint whisper, bridging the unimaginably hot singularity of the past with the vast cosmic web we observe today. What makes this relic truly extraordinary is how it transformed cosmology from speculation into precision science. Before its discovery, theories about the universe's origins often resembled philosophical debates, compelling narratives with little concrete evidence. The CMB changed everything, providing measurable data where once there were only educated guesses. Its temperature fluctuations act as a cosmic barcode, scanning the universe's vital statistics with error margins smaller than 1%. The near-perfect blackbody spectrum confirms the Big Bang's thermal history, while the acoustic oscillation patterns verify inflation's explosive growth spurt. Even the subtle polarization ripples may soon reveal gravitational waves from the universe's first trillionth of a second. This isn't just astronomy, it's cosmic archaeology, where microwaves serve as our shovel and light years our excavation site. Yet the deeper we look into this ancient glow, the more mysteries emerge. The cold spots chilling anomaly, the hemispheric asymmetries puzzling imbalance, the stubborn Hubble tension. These aren't flaws in our theories but guideposts pointing toward discoveries yet to come. The CMB doesn't just answer questions, it teaches us which questions to ask next. Perhaps future breakthroughs will come from even more precise polarization maps or from cross-referencing microwave data with gravitational wave observatories. One thing is certain, this primordial light still has stories to tell. As we conclude this journey through the universe's oldest light, take a moment to marvel at our privileged place in cosmic history. We exist in a brief window where the afterglow of creation remains detectable. Not so early that the universe was opaque, not so late that the CMB has faded beyond recognition. Our generation gets to study these photons just as they transition from microwaves into radio waves, like catching a sunset at its most vivid moment. The atoms in your body were forged in stars, but the quantum fluctuations that seeded those stars, they're right there in the CMB's patterns, meaning you're literally made from the same primordial ripples now mapped across the sky. So what do you think? Does the cosmic microwave background raise new questions about our universe's origins for you? Maybe you're curious about those unexplained anomalies or want to dive deeper into how dark energy shapes the CMB's evolution. Drop your thoughts below. After all, the greatest discoveries often begin with simple conversations beneath the same ancient light that's been guiding humanity's cosmic curiosity since the dawn of time. Whether you're an avid space enthusiast or just starting your journey into cosmology, remember, every time you look up at the night sky, you're not just seeing stars. You're witnessing the ongoing story of a universe that left its very first chapter written in microwaves, waiting for us to decode its secrets one photon at